Wasn't quite ready for prime time. We all have.
Happens more often than we'd like.
But what if I told you there's a whole world of really rigorous testing happening behind the scenes? Far beyond just clicking a few buttons.
Absolutely. There's a lot more to it.
Today, we're plunging into a pretty fascinating method called mutation testing.
Right.
Think of it as a clever way to sort of stress test our software tests themselves.
That's a great way to put it. Testing the tests.
The core idea. We kind of sneakily introduce little errors, faults into the code, just to see if our existing tests are actually sharp enough to spot them.
That's the crux of it, really. We're not just asking, does the software work? That's basic. We're asking the more probing question, are our safeguards, our tests, truly effective? Can they catch even really subtle flaws?
Okay.
So in this deep dive, we'll explore why this approach is so valuable, for ensuring software quality. We'll look at its purpose, how it actually works, step by step.
How you make these mutants.
Exactly how these intentional mutations are created. And, ultimately, what are the pros and cons of using such a detailed technique?
Okay, mutation testing. Intentionally breaking code. It sounds a bit counterintuitive, doesn't it? Like something you'd normally try hard to avoid.
Well, yeah, on the surface.
Okay.
But at its heart, mutation testing is a software testing technique where we deliberately make small changes. These are the mutations we mentioned to the original source code.
Okay.
The whole point is then to see if our existing test cases can actually detect these introduced errors. Think of your test suite, like a security system for your code.
Right.
Mutation testing is like trying to sneak past that system in various subtle disguises to see if it's truly vigilant.
So we're not trying to make the whole program crash and burn, then. We're talking really tiny, almost imperceptible alterations.
Exactly. The mutations are designed to be very small, single-focused changes. The goal isn't to cripple the program, but to inject subtle faults that a good, robust test suite should be able to identify. That's why it's also sometimes called fault-based testing.
Ah, okay.
We're basically creating faults on purpose to test the fault-finding capabilities of our tests.
Now, I see it's often labeled as a white box testing technique, and it's mainly used for unit testing. What does that tell us? Why those labels?
That's an important distinction, yeah. Because we're actually modifying the source code itself.
You need to see inside the box.
Precisely. You need to be able to see and access that code, hence white box. And because these changes are so granular, so small, focusing on individual lines or maybe small blocks of code,
Right.
It's most effective when you apply it during unit testing. That's where we're testing individual components or functions in isolation.
So you can pinpoint problems more easily.
Exactly. It lets us pinpoint exactly which parts of our code, and maybe more importantly, which aspects of our tests related to that code are working well, or maybe not so well.
It's pretty fascinating that this idea, you said it popped up way back in 1971, but then it sort of faded for a while before making a comeback. What happened there?
Yeah, the initial hurdle was mostly practical. Think about computing power back then.
Right. Not what it is today.
Not even close. The sheer computational effort required to first generate all these slightly different versions of the mutants, and then run all the tests against every single one. It was immense.
Just too slow, too expensive.
Incredibly time-consuming and resource-intensive.
Yeah.
But, fast forward to today with the massive advances in processing power and, crucially, the development of sophisticated automation tools.
Automation.
Mutation testing has become much more viable. It's practical now, especially for languages like Java and XML, where the tooling support has really matured.
All right, so we're intentionally tweaking the code. Let's get into the nuts and bolts then. How does mutation testing actually work? What are the steps?
Okay, so the process generally unfolds in about 5 key stages. First up, you have creating the mutants.
Making the faulty versions.
Exactly. As we've discussed, this involves introducing those small intentional faults into the original source code. This results in multiple, slightly different versions. And ideally, each mutant program contains just one single fault.
Why just one?
Well, it helps isolate the impact. If a test fails for a mutant with only one change, you know exactly what change caused it and what the test detected. If you put multiple changes in, it gets muddier.
Okay, makes sense. So the aim is that our tests should spot these single faults.
Right. The aim is that our test cases should be able to make each of these slightly flawed versions behave differently, produce a different result than the original correct code.
Okay, so step one, make mutants. We've got our original code and this collection of slightly broken versions. What's next?
Step 2 is applying the test cases. Pretty straightforward. We take our existing test suite, the same set of tests we'd normally run against our original program anyway,
The ones we think are good.
hopefully, and we execute them not just against the original, but against each and every one of these mutant programs we just created. The core idea here is that, good test cases are specifically designed to uncover errors.
And then step 3 is seeing if they did find the errors we planted, right?
Precisely. Step 3 is comparing the results. This is crucial. We look at the output or the behavior generated by the original program when it runs the tests.
Okay.
And we compare that side by side to the output produced by each of the mutant programs when they run the exact same test cases.
So a difference in output is what we're actually looking for. That's a success.
Yes, that's the goal. And that leads us straight to step 4, killing the mutants. If a mutant program produces a different output, or maybe it crashes when the original didn't for a particular test case, we say that the test case has successfully killed that mutant.
Like the test detected the disguise.
Exactly. Think of each dead mutant as a small vulnerability that your test suite has successfully identified and neutralized. The more mutants our tests kill,
The better we feel about our tests.
the stronger we can assume our testing safety net really is.
But what if the output is identical? What if the mutant gets away with it? It survives the test.
That's step 5, dealing with the alive mutants. If a mutant program produces the exact same output as the original program when run against our test cases,
Nothing different happened.
then that mutant is considered alive. And that's actually a red flag for our test suite,
Why a red flag?
because it suggests a potential weakness, a blind spot in our test cases. They weren't sensitive or specific enough to detect that particular fault we introduced.
So the test needs improving.
Right. In such cases, we need to go back, look at that alive mutant, understand the change we made, and then figure out how to write a better, more effective test case, or maybe modify an existing one that will be able to kill that mutant next time.
This sounds like a really rigorous way to evaluate how thorough our testing actually is. Okay, let's dive a bit deeper into creating these mutant programs. You said small, single changes. What kinds of changes are we actually making to the code?
Yeah, so a mutation in this context is really just a single, small, syntactic tweak or alteration to a statement within the program's source code. The guiding principle, as we said, is that each mutant version should differ from the original code by only one such change.
Can you give us a really concrete example, something simple to picture?
Absolutely. Let's imagine a really simple line of code in, say, Java or Python. Maybe it's if price 10.
Apply it.
Okay, if the price is over 10, apply a discount.
Right. A possible mutation here could be just changing that greater than operator to a less than operator. So the mutant code becomes if price 10, apply discount.
Ah, okay.
Now, the idea is that a good set of tests for the original code should probably include a test case where the price is, say, exactly 10 or maybe 11.
Boundary conditions.
Exactly. In the original code, a price of 10 doesn't trigger the discount. In the mutant code, it also wouldn't. But what about a price of 9? Original code, no discount. Mutant code, discount applied.
So if my test didn't check twice below 10, then that mutant would produce the same result as the original for all your existing tests, and it would remain alive. That immediately highlights a potential weakness, right? Your tests weren't checking that lower boundary condition properly.
Okay, that makes it much clearer. So are there common categories of these code alterations, these mutations that people typically use?
Yes, definitely. We can broadly group them into a few types. One common category involves operand replacement operators.
Changing the data bits?
Sort of. It's where we substitute one variable or value with another. So maybe replacing a variable x with another variable y in an expression, or even replacing a variable with a specific constant value. Like if you had if count 0, a mutant might be if 5, 0.
I see.
Another big category is expression modification operators. Here, we're messing with the operators themselves.
Like the greater than becoming less than.
Exactly. Or changing an equality check, like x equal y to maybe a greater than or equal to check, x, y.
Oh.
Or you could even insert new operators, like changing x, y into x plus y, introducing a pre-increment.
Oh, that could have subtle side effects.
Definitely. And then a third category is statement modification operators. This is a bit broader, where we alter entire program statements.
Like deleting a line.
That's one possibility. Or maybe removing the else part of an if-else structure to see what happens. Or sometimes even deleting an entire if-else block just to observe how the program behaves without that logic.
Wow, okay. It sounds like there's quite a range of potential modifications you could make. Are there, like, standard lists of these mutation operators that developers use?
Oh yeah, there are established sets of these operators. Some
Mhm.
common examples you might see used by the tools include things like GOTO label replacement. That's maybe more for older languages.
Right.
More common now would be return statement replacement, like changing return X to return 0 or something. We
Hmm.
mentioned statement deletion. Also, unary operator insertion, adding those plus plus or operator.
Hmm.
Then there's logical connector replacement, changing an A and D to an OR in a condition, which can drastically change logic. Maybe comparable array name replacement. We talked about removing the else part in if else.
Yep.
Adding or replacing arithmetic or relational operators is a big one. You can also have statement replacement by just changing the data used in a statement, or direct data modification for variables, like changing x to x to x equals 0. And sometimes even altering the data types of variables, though that can sometimes cause compilation errors rather than subtle runtime differences, which isn't always the goal.
This level of detail is really impressive, but it immediately brings a big challenge to mind. The sheer volume of possible mutants. It just seems overwhelming. How could you possibly handle all of this manually? It feels impossible.
You've absolutely hit the nail on the head there. Manual mutation testing is, for all practical purposes, infeasible for any real-world software project of decent size.
Just too much.
Way too much. The number of possible single changes, potential mutants, can explode very, very quickly, even for relatively small pieces of code. A simple function might generate dozens or hundreds of mutants, a whole class, thousands.
So automation is key.
It's not just key, it's absolutely critical. It's essential.
Yeah.
We heavily, heavily rely on specialized automation tools to do the heavy lifting.
The grunt work.
Exactly. These tools handle generating the mutants based on predefined rules or operators. They automatically run the entire test suite against the original code and against each and every mutant.
Wow.
And then they analyze the results, count the killed versus alive mutants, and generate a report, often including that mutation score we'll talk about. This automation is what makes mutation testing actually practical and somewhat cost-effective in modern software development. Without it, it would just be an academic exercise.
Are there any specific tools that people listening might have heard of or could look into?
Yeah, definitely. In the Java world, PIT testing, sometimes just called PIT, is a very well-regarded and powerful mutation testing framework. It's widely used.
Okay, PIT for Java.
And if you're working more with JavaScript, TypeScript, or other web-related technologies, then Stryker or Stryker.js is a really popular and effective option. There are versions for other languages, too, under the Stryker umbrella.
Stryker, got it.
These tools basically take care of that whole process we described: generating, running tests, comparing, reporting.
We briefly touched on different kinds of mutations earlier, operand changes, statement changes. Are there also distinct high-level types of mutation testing itself, different approaches?
Yeah, at a fundamental level, you can kind of categorize mutation testing into three main types based on what's being changed. There's statement mutation, value mutation, and decision mutation.
Okay, what's the difference?
So statement mutation, as the name suggests, focuses on making changes to entire individual code statements. An example might be accidentally deleting a line of code or maybe duplicating a line through a bad copy-paste. Mutation testing can check if your test would catch such structural changes.
Right.
Value mutation is more about altering the specific values of data used within the code, like variables or constants. For instance, changing a hard-coded threshold value from, say, 10 to 11, or a Boolean flag from true to false.
Okay, changing the numbers or states.
Exactly. And finally, decision mutation specifically targets the control flow logic of the program. This means altering the conditions inside, if statements, while loops, things like that, changing by 5 to x equals 5, for example. These directly impact how the program makes decisions and follows different paths.
Gotcha. Statement, value, decision, different focuses for the mutations. So we have a way to create these flawed code versions, the mutants. We run our tests against them. We see how many we manage to kill. How do we then, put a number on it? How do we quantify the effectiveness of our overall testing effort using this method?
Right, that's where the mutation score comes in. It's the primary metric used in mutation testing. And it's actually a fairly simple calculation.
Yeah.
You just take the total number of mutants that your test case has successfully killed.
The ones that produce different results.
Exactly. You take that number and you divide it by the total number of mutants that were generated in the first place, killed, plus alive mutants.
Right. The whole population.
Your whole population. Then you just multiply that result by 100 to express it as a percentage. So, killed mutants, total mutants, 100.
So, obviously, a higher percentage on the mutation score is what you're aiming for. That means your tests are doing a better job.
Exactly right. A mutation score of 100% is the theoretical ideal. That would signify that your test cases are considered mutation adequate, which is the technical term.
Mutation adequate. I like that.
It means they were able to detect every single one of the simple syntactic faults that were injected by the mutation process. Now, achieving a perfect 100% can be quite challenging in practice and sometimes not even necessary or cost-effective.
Because some mutants might be equivalent. Like, they don't actually change the behavior.
That's a very good point. Sometimes a change creates an equivalent mutant. The code is syntactically different, but semantically it does the exact same thing as the original. Those can never be killed. Good tools try to detect and ignore these, but it's a hard problem.
Oh, okay.
But even with that caveat, research and lots of real-world application have consistently shown that mutation testing and striving for a high mutation score is a very valuable method for gauging just how robust and comprehensive your test suite truly is. It often finds weaknesses that simple code coverage metrics miss.
But the big drawback remains.
The main practical limitation, as we've discussed, in striving for that really high score is definitely the potential cost and the time involved, especially in generating and then executing tests against potentially thousands or tens of thousands of mutants.
Okay, let's try and sum up the key benefits then. Why would a development team go through all this effort? What are the major advantages?
Well, for starters, it's an incredibly powerful way to achieve very high coverage of your source program, often forcing you to test paths and conditions you might have missed.
Goes beyond just line coverage.
Much beyond. Because you're essentially testing against so many slightly different versions, you're really forcing your tests to exercise more of your code base in a wider variety of subtle scenarios. This leads to thorough, comprehensive testing of these mutant programs, going significantly beyond just testing the original happy path functionality.
Okay.
It also provides incredibly valuable feedback for developers, not just on the quality of their production code, but crucially on the effectiveness and completeness of the tests they've written for that code.
Helps improve the tests themselves.
Absolutely, that's a primary goal. Furthermore, mutation testing has this sort of unique ability to uncover ambiguities or subtle edge cases within the source code that might not be apparent through more traditional testing methods, like just checking coverage numbers.
Finds the sneaky bugs.
It has the potential to detect a very high percentage of actual faults that could exist in the program because the mutations often mimic common programming errors. And ultimately, by driving the creation of better tests and therefore more robust and reliable software.
It helps the users.
Exactly. It directly benefits the customers or end users by leading to more stable and dependable systems they can rely on.
Those are some pretty compelling pluses. Now let's be realistic. Got to look at the other side. What are the main drawbacks, the limitations we need to keep in mind?
Yeah, definitely not without its challenges. On the flip side, the main disadvantages really revolve around cost and the time investment required. That's the big one.
Expensive.
Mutation testing can be extremely expensive and time-consuming, especially for larger, complex code bases, simply due to the potentially vast number of mutants that can be generated and need testing.
Right.
As we've stressed multiple times, it virtually necessitates automation to be practical at any kind of real scale. Doing it manually is just not feasible.
And the automation itself isn't free either.
Good point. Setting up the tools, integrating them into the build process, interpreting the results, that all takes effort too. Another key contributor to the cost is the fact that each individual mutant often needs to be tested against the entire suite of relevant test cases designed for the original program component.
So if you have 100 tests and 1,000 mutants,
you could be looking at 100,000 test executions roughly. That can lead to a massive overall testing effort and significantly increase build times.
Wow, yeah.
And finally, just to reiterate, it's important to remember that it's fundamentally not applicable to black box testing methodologies.
Because you need the source code.
Exactly. Since it inherently involves examining and modifying the underlying source code, you can't use it if you're only testing from the outside without access to the internals.
So, wrapping up, while it's clearly a really deep and potentially very effective method for making sure our tests are actually doing their job properly, it definitely demands a significant commitment of resources, time, computing power, and it really relies heavily on having the right automation tools set up and working well.
Precisely. It's a classic trade-off, isn't it? You're trading implementation complexity and runtime cost for a much deeper level of insight into the true effectiveness of your tests and higher confidence in your code's quality.
This has been an incredibly insightful look into the world of mutation testing. Really fascinating stuff. It's clear that making sure software works reliably involves a whole lot more than just, running the program a few times and seeing if it crashes.
Absolutely.
Mutation testing offers this powerful, though admittedly demanding, approach to truly validate the strength of our testing efforts themselves.
It truly does. And while that initial investment in time, setup, and compute resources can seem significant, the increased confidence it provides in the reliability and robustness of our software, specifically by rigorously examining our own testing processes, is often seen as a very valuable outcome in critical systems.
It makes you think. Consider the implications of having such a detailed, almost microscopic understanding of how well our safety nets are working in the complex world of software.
Yeah.
What if we applied this same level of intense scrutiny, this kind of mutation thinking, to the ways we validate other important aspects of our lives, our decisions, our systems?
That's a really interesting thought.
It kind of prompts you to think about how we truly ensure things work effectively, how we test our assumptions, in all sorts of contexts beyond just code, doesn't it?
It certainly raises important questions about verification, validation, and how we build and maintain trust in the complex systems we rely on every day. A lot to ponder there.
Indeed. Well, thanks for taking that deep dive with us today. Really illuminating.
My pleasure. Always interesting to talk about.
And thank you for listening. Until our next episode.